Hi, and welcome to this solution video for this first module of computational quantum mechanics problems. First off, I want to just say that we're working in a Google Colab environment. Google Colab is a website where you can run Jupyter notebooks, nice and easy. So there's a bit of a catch though. Every time you start up a Colab notebook, you might have to install some Python packages if they're not built into Colab. So, for instance, we will be using ComFiT to run quantum mechanical simulations. So, the first thing I do when I start up this notebook is I run this. I already ran it, so it will be quick for me, but for you, it might take a couple of seconds. All right, so let's get started. The goal for this module is to run some numerical simulations of the Schrodinger equation for a single particle in 1 dimension and 2 dimensions. And we want to build some intuition for what solutions to the Schrodinger equation can look like. Additionally, we want to compare the classical and quantum mechanical solutions to a particle in a harmonic potential. All right, let's get started with the first problem. So for the first subproblem, we just want you to write up the time-dependent Schrodinger equation for a single particle in 1 dimension and 3 dimensions. And this should be quite straightforward. The difference between the 1-dimensional Schrodinger equation and the 3-dimensional Schrodinger equation is that this d squared by dx squared is replaced by the Laplacian. And just remember to define all the quantities. So h bar and I the imaginary unit, and v the external potential, and psi the wave function, and so on. All right. So for the third point on this problem, we ask you to think a bit about how you can plot a complex function in 1 and 2 dimensions. So some ways you can plot a function from the real numbers to the complex numbers. Well, one way you can do it is you can plot the absolute value along the y-axis. And then just essentially you're doing the same as plotting just a real function, where you just discard the phase information. And you can add in the phase information just as a color that you add to each of the points. So that's one way you can do it. You can also plot the real and imaginary parts separately. For when moving to a function from the real plane to the complex numbers, you can give each point in the plane a pixel intensity according to the absolute value of the complex number that you assign to that point. And you can give a color according to the phase. That's one way you can do it. Or you can use color to encode phase and contour lines to encode the lines where the modulus is the same. You can also just plot the intensity of the real part using color, and do the same for imaginary parts. You can plot those two separately, or you can just look at some cross-section of interest and plot that. So these are just some suggestions. Creativity is very welcome here, so feel free to think about some more creative ways you can plot some complex functions. All right, so for the second problem, we'll get started with running some simulations. So here we initialize the system with a time step of 0.1 with bounds of a lower bound in x direction of -10 and an upper bound of 10. And this one right here just signifies that it's a 1-dimensional system. This line right here initializes the wave function to be a Gaussian. And here we just read out the wave function and store it in the variable psi. You can use the psi, or you can just access the wave function directly from qm.psi. All right, so now for the problem, we want to use the functions plot field and plot complex field to plot the wave function and the probability density for finding the particle. And we want to run a time evolution using the method evolve Schrodinger. And we want to plot the wave function probability density after evolving the system. And then we're supposed to discuss what we see. All right, so let's plot the initial wave function. All right, so it's centered at 0. It's this nice Gaussian curve as we initialized right here. The Q plot complex field function is quite nice because as we discussed before, we use this method of plotting a complex function where the absolute value is on the y-axis and the color encodes the phase information. So in this case, the phase information isn't all that interesting. It's all just constant phase of 0, so it's all just a positive Gaussian curve. All right, cool. So next, we compute the probability density. So that's absolute value squared. And then we use plot field to plot this real function. All right, let's see. So it's got the same shape, except it's a bit narrower because we're taking this square to get the probability density. That all makes sense. All right, so let's run a time evolution. After the time evolution, we plot the resulting wave function, and we get this thing. We see that the wave function here has spread out compared to the initial wave function. And also, it's picked up a bit of a phase gradient, so the phase changes. All right, let's also plot the probability density, and it's also spread out. So what does this tell us? It tells us that initially, if you were to check the probability of measuring the particle at x equals 0, that's higher in the beginning than after a bit of a time evolution because the probability distribution is spread out. On the other hand, after a bit of time, the probability of measuring the particle at x equals 4, for instance, a bit further out, is going to be higher after the time evolution. All right, awesome. Let's move on to the third subproblem. So in this problem, we're just supposed to repeat what we did in B, essentially just plotting the wave function. But we do this for a wave packet with initial velocity 1. And the way we set this initial velocity is we send in this keyword argument into this function conf initial condition Gaussian, which sets up the initial wave function. So let's just do that. Shouldn't be too hard. All right, let's plot the initial wave function. It's the same as before, except it has a bit of a phase gradient. So we see the phase changes. It's not uniform as it was in the previous example. We plot the probability density, and that's the same as we had for just still momentum 0 Gaussian. Or velocity 0 Gaussian. And we do the time evolution. We plot. We see that, well, it has momentum, so it's moved in positive x direction. And also we can note that it's picked up a higher phase gradient on the right hand side, and maybe a bit of a lower phase gradient towards the left hand side. So let's take and plot this probability density as well. And we see, it's the probability density is spread out and it's moved to the right, which is essentially what we expect. Cool. So when we have momentum, we still get this effect of the wave packet spreading out, but it moves to the right in our case. All right, cool. Now, for the second problem. In this problem, we will run some simulations of the two-dimensional Schrodinger equation for a single particle. We again initialize a Gaussian wave packet, this time with this initial velocity 1, 0. And for this problem, we're supposed to plot the initial wave function, run the time evolution, plot the resulting time wave function after the time evolution. And then we're supposed to repeat this for a different initial velocity. And then we're supposed to give a brief comment on how these results relate to the de Broglie wavelength. All right. So we can still use these same methods for a complex field. They work for two-dimensional systems as well. So this should be pretty much the same as the previous problem. The point here is just to give you some visual intuition for how these solutions behave. All right, so let's plot the initial wave function. We see, well, we have this Gaussian here, where the intensity of the pixel signifies the absolute value of the complex amplitude. So here we see that since we have an initial velocity of 1, 0, so that's a velocity to the right in this case, because this is the x-axis, we get a phase gradient going in this direction. So what do we expect then? Well, we expect the particle to move in this direction as well. So let's run time evolution to see if that is what happens. So we run the time evolution. We see, indeed, it starts moving in positive x direction, and the wave packet starts to, I mean, it bends off. So it has these like these circular lines and bends off and moves to the right. Okay, cool, interesting. Let's just repeat this for initial velocity 1, 1, and plot here. Right, and we see the same thing. The initial wave function has a phase gradient in the direction 1, 1. So the phase changes in this direction right here, and we run a time evolution, and we see that it bends off. And if you plot the probability density, you'll see that it moves in the direction of velocity. All right, cool. Additionally, we have some code here for generating animations. This takes a bit of time to run. I've pre-run it for this setup with initial velocity 1, 0, and I'll show it to you right here. So, right, we see what we expect. The particle moves in positive x direction, right? It's cool to have these animations making these things a bit more concrete. So I'd recommend, if you had some system that you'd like to study, you can play around with the initial velocity. You can play around with the potential that we're working in, and you can generate these time evolution plots as you like. So feel free to play around with this. All right, for the third problem, we'll go into we'll examine the time evolution of a Gaussian wave packet in a 2D harmonic potential. So we will compare the time evolution of the wave packet with just the classical trajectory of the particle. So in our case, the harmonic potential is given by half k x squared plus y squared, and we will use the value of k equals 0.01. And for an account of the units used, you can go to this page right here and have a look. So for the first subproblem, we ask you to just describe a numerical algorithm you can use to compute the classical trajectory of a particle in this potential. So we are using units where the mass equals 1, so the acceleration just becomes the negative gradient of the external potential. So if you compute the negative gradient of this, it just becomes half k xy. And so in order to numerically compute the time evolution, we just do forward Euler. So this gives this integration loop right here. We update the acceleration as minus k times the position, which is just the negative gradient of the potential. We update the velocity as v plus the acceleration times the time step. And we update the position as position plus the velocity times time step. And this is just a simple forward-Euler integration loop. So in the next problem, we will actually run these numerical simulations. Both the classical system using this integration loop we've specified here, and of the quantum mechanical system using ComFiT. All right, so let's set up our system. Here, we set the time step to be 0.1. We initialize a two-dimensional system with bounds of minus 30 and 30 in the x direction, and minus 30 and 30 in the y direction. And we set the initial position of the particle to be 5,5, and we set k equals 0.01. So, additionally, we set the external potential, and we configure the initial wave function right here. Cool. So in this problem, we concretely ask you to numerically compute the classical path of the particle, and we ask you to numerically solve the Schrodinger equation using ComFiT, using the same initial position and velocity. And then you're supposed to plot the solutions after times 0, 5, 10, and 20, and then discuss a bit. So I've created this little function which performs the time evolution for the time t. And so here you see the classical time evolution. So this is just a forward Euler integration loop. We set the initial position and velocity, and we just use this algorithm that we specified in the previous subproblem. And then right here, we use the method qm.evolve Schrodinger to evolve the quantum mechanical system. We then use qm.plot complex field to plot the wave function after time t. And then we use this figure.addTrace, which is plot-B syntax for adding in more to a plot, where we add in this scatter plot, where the point that we add in is just the position of the particle right here. So this is the structure of the code. Now let's see what we get. No, sorry, I need to run this first. Let's see. So after time 0, so initially the particle has 0 velocity, so it just has a constant phase, and the classical solution is just right in the middle of the quantum mechanical wave function. So let's see what happens after time t equals 5. We see that the wave function starts to move in towards the center of the potential. So mind you, this is a harmonic potential which has a minimum right in the middle right here. So this makes sense. The wave function starts to move in towards the middle. We see that the classical solution starts to follow along, and it approximately tracks the part of the wave function that has the highest probability density. Yeah, just heuristically looking at the intensity of the colors. So let's plot after time t equals 10. And we see, the wave function is moved even further towards the center. It has a lot of momentum, which is encoded in this phase gradient right here. And after time equals 20, you see that it's moved all the way over here, and it's curving the other way. So so naturally the quantum mechanical solution is gives a probability density, so it's spread out, whereas the classical solution is just a point. All right, makes sense. We also have this code that I introduced previously for generating animations. This line took a bit of time to run, but I'll just show you the result. So I got this nice plot of the wave function as it evolves according to the Schrödinger equation in this harmonic potential. So let's see how it looks. Isn't that nice? Starts at the point, moves over to the other side of the potential, concentrates on that point, and then moves back. Super nice. All right. So feel free to play around with the code and set up your own potential. You can essentially just change this external potential to whatever you like and play around with the solution, generate some animations. Yeah, have fun with it. All right. Hope you have a nice day.